Hello, everybody. My name is Phil Lamar, and you are watching NASA's Ask the Astronomers Live, where we ask real live astronomers, not a Google search algorithm, questions about some of the most amazing things in the universe. Today, we're going to be turning our attention to why it matters to look up and search for potentially hazardous objects that could possibly hit our planet. Now, for those of you joining us on Facebook or YouTube and watching the live stream there, please, you've got the chat there, use it. Say hello, ask questions, ask us which direction you should be looking up, things like that. And afterwards, make sure to visit our website, universeunplugged.org, where you can watch all sorts of great, fun astronomy videos and find out about our upcoming episodes of this show and many other shows. Right. So our guest today will tell us why we do look up and what they find when they do look up. Sometimes it's objects that might prove to be hazardous to Earth, but I'll let them tell us about that. So today, we're lucky enough to be joined by astronomers Amy Meinzer and Joe Massaro. Welcome, Amy. Welcome, Joe. Good to see you.
Hey, thanks.
Now, because some people out there think of astronomers as just science with shoes on, but in fact, astronomers are people. Why don't you guys tell us a little bit about yourself and your work, your background, whatever you're working on these days, whatever you want. Amy?
Sure. Yeah. Well, let's see. My name is Amy Meinzer, as Phil mentioned, and I'm an astronomer. Actually, I'm a planetary scientist at the University of Arizona. So I am a professor there, and I study near-Earth asteroids and comets, as well as the asteroids and comets that are a little more distant in our solar system. Let's see. For hobbies, what do I like to do? Oh, I like to bird watch. Actually, there's something about watching moving objects, whether they're in space or on our Earth, that's really fun. So I love watching birds, and I like to roller skate in my spare time.
Oh, there you go. See, that's very human. Joe, tell the folks. I mean, you've been on the show before, so it's good to see you again.
I have. Yeah, it's great to be back here. So I'm Joe Massaro.
But for the folks that we're probably getting a lot more people watching because we've got that great "Do Look Up" graphic. So they may not have seen your earlier show. Tell them about yourself.
Sure. My name's Joe Massaro. I'm a solar system scientist at IPAC at Caltech. My studies focus mostly on the physical properties of the small bodies of our solar system, the asteroids and the comets. I like to figure out what they're made of, where they came from, where they're going, and what that tells us about how our solar system formed, how it was constructed, how it was ripped apart, and some of those pieces were ripped apart and turned into groups of asteroids. And so that's what my most of my work focuses on. I also have a small, a special place in my heart for asteroid polarimetry, and that's been one of my latest things I've been working on, which is how light gets polarized when it bounces off of these asteroids. And in terms of my hobbies, well, in grad school, I picked up playing the bagpipes, and so that's been a thing I've been doing on and off ever since then, and it's a lot of fun.
Oh, that's great. Well, and I guess because nothing's been hitting the Earth lately, you guys have time to skate, bird watch, play the bagpipes, right?
Yeah. And I think, Joe, for a while, you were practicing bagpipes in the Caltech parking garage, right? I remember hearing
Yeah, for a few years I would go down there and go to the underground garage on weekends when it was empty and play down there. And then nowadays I'm off in Griffith Park.
Echo effect?
Oh, it was great acoustics in there. Yeah, I mean, it just rang. People would stick their heads down like, what's going on down here?
Who's honking? Wait, Joe, you just mentioned, did you say polar telemetry? What was it?
Polarimetry. So it's the polarization of light. Like, how polarized sunglasses block out light that bounces off of water? Same kind of thing. You can do that. You can put one of polarized sunglasses effectively in front of your telescope and look to see how the light's bouncing off of the surfaces there. And so it tells you something you don't get in any other way.
Got it. All right. Thank you.
Yeah.
Now, I guess we should start with the movie that just came out recently, Don't Look Up, about a comet that's on its way to hit the Earth. Now, I mean, that's obviously fiction, but Amy, could that actually happen? Could we get
Well,
wiped out by a comet?
so it's an interesting question. I was actually the science advisor on the movie. And the good news is we really don't know of any giant comet that's about to smack into the Earth. So that's the great news. So right off the bat, the movie is firmly in the realm of science fiction, if you want to think of it that way, which is a really good thing. That said, our planet actually has been impacted by comet, or an asteroid or a comet that was of the same sort of size as the object that's shown in the movie. And that was the object that we think that wiped out the dinosaurs 65 million years ago. And so there's plenty of evidence for these large impacts on the Earth. But the good news is they tend to happen very, very, very infrequently. So you can kind of think of it this way. Human life probably wouldn't be here on planet Earth if we were constantly getting bombarded by really big impactors. So we know that it's not a very common event. That's the good news.
Okay. Oh, so you were the science part of the science fiction of Don't Look Up.
Yes. Yeah. It was really good
Okay.
to work on it. It was a really interesting experience. And one of the things that's always challenging with science fiction movies is, of course, you're depicting things that haven't really happened in real life or that aren't about to happen. So how do you draw a boundary between, what is real and what is real science and where we go off into the realm of fiction? So it was a lot of fun to work with the team on this particular movie, just because science is kind of one of the main characters, if you will, in the movie in a certain sense. So it was a lot of fun.
Right. Well, it's interesting because I feel like a lot of the work that you guys do dealing with space is about predictions, looking at patterns and then, think, okay, this is what may happen,
Right.
based on what we know. So I would imagine as a scientific advisor on a movie, there's a lot of that. It's like, well, in your fictional circumstance, this is what we think might happen if it were real,
Right.
based on what we know.
That's exactly right. And science is always dealing in probabilities, right? And that's another thing that's kind of hard, I think, when we talk to people, is that a lot of times we'll give an answer in terms of a probability. And even when something is really, really certain and very likely to happen, we still express it as a probability. And sometimes that's a bit of a source of confusion, I think.
Right.
We do touch on that a little bit in the movie.
Yes. Well, I always like to joke, that's the difference between science and religion. No one says 70%, gospel. Now, you said we know that there isn't anything that large, like in the movie, coming at us. How do we know, Joe?
So we've actually have been looking up with surveys for quite a while now. So back in the 90s, they were the first generation of surveys looking for some of the biggest asteroids. And we've moved on to another generation of surveys that's been looking for smaller objects. And we found at this point over 90% of all of these dinosaur killer scale or global event scale objects. One of the surveys doing this search is the NEO mission that Amy and I have been working on since 2009. Well, she's been working on longer than that, but I've been working with her on it since 2009. And that's using a space telescope that searches in the infrared for objects. But you can do a visible light telescope on the ground, an infrared telescope in space. Either of these will help you find objects and track them. And as you measure them, you get their orbits. You get to watch as they go around the sun, and you can determine whether or not it's going to hit us. So we know, as I said, of most of the big ones and not as many of the small ones. The smaller you get, the harder they are to find. And when you get down to something the size of a house, it's really tough to find these. And they can surprise you, like what happened in Chelyabinsk, Russia in 2013. If you can pull up image 1, a small object, as I said, 10, 15 meters in size, came in and exploded in the sky above the city. And that was too small to be found by our current surveys. But as we discover more of these and as we build new survey capabilities, we'll be pushing to smaller and smaller objects.
I see. Now, you mentioned that you guys are working on NEOWISE.
Yeah.
Is that an acronym?
Boy, it sure is. We love our acronyms at NASA. This stands for Near Earth Object Wide Field Infrared Survey Explorer. Let me catch my breath.
Yeah.
It's kind of a long one. So it's actually a double acronym. It's the Near Earth Object and then Wide Field Infrared Survey Explorer. And
Yeah,
we
there's
have
NEOWISE.
there we go. There's a picture of it. Yeah, it's an Earth orbiting telescope And it has a telescope that is kept extremely cold because it is searching for the very faint heat signatures that come off of asteroids and comets.
Right.
So in other words, what happens is the sun hits these asteroids and comets, and some of it bounces off the surface, but some of it's actually absorbed by the object. And by the laws of conservation of energy, that energy has got to go somewhere. And what happens is it gets re-radiated out into space, and we sense it as heat when we can see that with the telescope here.
Got it. Okay, so NEO, near Earth objects, that's something that can apply to comets, asteroids, the small thing that went over Russia, even something that small, is that considered a near Earth object?
Oh yeah, I got very near.
The nearest
got
near.
so near it landed in our hands. So this is actually a piece of that one.
Oh, you got one. Hey, I've got one. Yay. Hey. Okay, so here's some little pieces of Chelyabinsk right here that you can see.
No way.
And they're really fun to look at, and they're interesting. So yeah, look at how there's sort of a crust on the outside of both of these pieces you can see, but on the inside, if you look at this one, you can see the inside is the sort of grayish color rock. Well, that outer crust is called a fusion crust. It's basically the outside of it got burned as it passed through the Earth's atmosphere at very high speeds.
Yeah. And
Joe,
so,
how fast was it going? It was going really fast.
20, 30 kilometers a second or something. Usually most of the
Wow.
stuff that enters impacts around that speed. Gets pulled in by that last pole of Earth's gravity. Earth actually speeds them up as they come in. So yeah.
And it was probably the speed and the heat that made it explode in the air instead of hitting.
Yeah.
Yeah.
It was the pressure. The air pressure actually was squeezing it, and it just exploded.
And you know, when you hit the atmosphere at that speed, the atmosphere is really like a brick wall, basically. And but this object wasn't very big. It was about originally it was about somewhere around 17 to 20-ish meters across. So kind of a small building. But basically, most of it got destroyed by the Earth's atmosphere. It was small enough that it mostly just sort of exploded tens of kilometers up in the upper atmosphere. But the pieces that made it to the ground are these little bits and pieces like Joe and I have here. But there wasn't a big central crater that was left from a main mass that fell. So the object was small enough that it wasn't able to make it through. But if it's a little bit bigger, you get a different answer.
Right. Oh, fascinating. Well, speaking of answers, we actually have a question from Stacy DeVoe. Ooh. Now, this is a good question. Wouldn't an asteroid do more damage than a comet, since comets are more icy? Seems like they'd mostly melt. Oh, this is sort of what we were just talking about. What happens upon entry? You know, if it breaks down, does a comet break down? Theoretically, would a comet break down more on entry and maybe just turn into rain by the time it hits us?
Yeah, I mean, it absolutely, like, there's very big differences between asteroids and comets, but it tends to be structural more than compositional. So we used to think that comets were ice block, just big ice cubes, and asteroids were rocks. And as time has gone on, we've realized it's a continuum, right? That there's a little bit more water, a little bit less rock, and even things like the comets that are visited by spacecraft look to be a lot of rock, but it's not rock like you get on Earth, right? It's not like this thing that has been compressed by 4.5 billion years of geology into a solid object. It's crushy, it's fluffy, it falls apart, and so the difference between the impact might be whether you get hit by something that's made of iron and so acts like a bullet, or you get hit by something that immediately, as soon as it hits the atmosphere, shatters into a billion pieces and causes a different kind of impact, one that explodes in the air, for instance, like what happened in Russia.
Right. Oh, wow. Now, compositionally, the meteorites that you guys have, is that made up of something that exists on Earth, or is it a different?
Yeah, I mean, broadly speaking, it's rocky material. So this Chelyabinsk piece here is made out of a rocky type of material. Now, it's not exactly the same as the rocks that we find here on Earth, though, because these are leftover pieces from the formation of the solar system, and they haven't undergone, in general, the kind of geology and weathering and processing that the rocks here on Earth have experienced. So these are really kind of, in a way, very pristine pieces, some of them, because they're so old. I got another one here that's sort of an interesting study in contrast. Oof, I don't know if you can tell how heavy this thing is just from trying to lift it up, but this is a piece of a meteorite called Canyon Diablo. And this particular thing is a big chunk of nickel iron, basically. So unlike the little rockier piece there that you saw, this one is mostly metallic. And when this thing landed, this actually was only a little bit bigger than the Chelyabinsk asteroid. Instead of about 20 meters across, this was originally part of a rock that was about 50 meters across, so just a little bigger. But it left a kilometer-wide hole in the ground in the desert in Arizona. So that's a pretty big difference.
Yeah, that's amazing. Where do these... Oh, wait, we have another question. Oh, about Tunguska.
Right.
The meteor strike in 1908. Is that something we know about, or is that
we know
theory?
We know something happened, right? We know that there was a giant blast in the sky that leveled trees for 30 kilometers around this area. That many reindeer were killed by the blast wave, and it looks like this kind of airburst impact. Like I was saying, when you have something weak that comes in, the pressure is such that it just gets ripped apart and it explodes in the sky. And instead of hitting the ground like Canyon Diablo did and leveling out, ripping out a crater, it instead explodes, and that pressure wave rains down and blows down trees, and if it's over a city, buildings. So it can have a much broader effect when you have this explosion in the sky above. But yeah, no, that's another very good example of a near Earth object coming to visit us.
Yes.
Right. Okay. And yes, just a variety of impacts. And now you guys have those meteorites. Where do these near Earth objects, including the ones in your rooms, where do they come from?
Well, that's a really good question. Joe, do you want to take this one?
Oh, you got it.
Okay. Well, in general, I mean, most of the small bodies in our solar system, we have a big band of them between Mars and Jupiter called the main asteroid belt, and that's a pretty stable place. If you're an asteroid, you mostly just stay there, going around the sun for billions of years, perfectly harmless, nothing going to happen. But there are some exceptions. Eventually, what can happen to these asteroids is that they can collide with other asteroids and they can create showers of fragments. And then sometimes what can happen is, under the very gentle pressure of sunlight, actually, they can slowly drift into what we call resonances. So we have planets in our solar system. And if you're an asteroid that gets into a certain type of orbit that is resonant with one of the planets, that can have a really dramatic effect on your orbit. And now all of a sudden you can get slingshot into the inner part of the solar system, just like hitting a flipper on a pinball machine on astronomical time scales, of course. Not human time scales, but on astronomical time scales, it goes really fast. So for us, that's like millions of years. Oh yeah, and here's a great graphic that kind of shows what we're talking about. What basically means that something can transition from being a main belt asteroid, so orbiting outside the orbit of Mars here, and then it can come into the inner part of the solar system, becoming what we call a near-Earth object. And Phil, you talked about this, right? These are the asteroids and comets that get somewhat close to the Earth. So NEA there is near-Earth asteroid.
And what's a PHA?
Well, that's another category. So this is a category. Joe, do you want to take this one? What do you think?
Sure. Yeah. So PHA we use to stand for potentially hazardous asteroid, and so it's also a near-Earth asteroid, but it is one that has an orbit that comes close to Earth's orbit, within 5% of an astronomical unit. So 1 AU is the distance from the Earth to the Sun. Within 0.05 AU, if the two orbits, those two little lines, are that close, it's something that we want to pay extra special attention to. And that's because the orbits can change subtly over time because of the gravity of the planets. So if you've taken high school physics, you learned how to write the gravity equation and how to calculate the gravitational attraction between two things. And it's a real simple equation, and it's really easy to put down, and you get a quick answer, and it makes for very nice orbits. But as soon as you add a third body, something else massive, like a planet, like Jupiter, like Earth, like Mars, it becomes a chaotic system. And so what was a very simple equation becomes effectively impossible to know for forever in the future. And so we can model short-term changes, and we can look over the span of hundreds or maybe 1,000 years, but after that, it just gets chaotic. And so these are the objects that are close enough to the Earth's orbit that we really want to pay attention to them on that 100-year timescale.
Got it. Okay, great. Thank you, Joe. That because Amy, what you were saying, it made me wonder, because I was thinking, like Joe was saying, like high school physics. But wait, how do things collide if they're in orbit? Don't they just go in a circle? But
Yeah,
you're adding other
Yeah.
gravity. It's not just the one circle. Something can pull it out of its
Exactly.
original orbit.
yeah, it
And
gets crazy fast.
Yeah.
right,
It gets really
you never know
complicated.
what's going to happen. Wow. Okay, wait. Let me just we're in case anybody is joining us late or missed our introduction. This is Ask the Astronomers Live, and we're here with Dr. Amy Mainzer and Joe Massaro, and we're talking about near-Earth objects and whether we should duck. And those of you watching us live on Facebook or YouTube, please say hi or ask a question. You got the chat right there. Use your fingers. Okay. Now we've got a few questions here. Oh, here's another question. Great. Thank you, Stacy. Is it safe to say that it's inevitable that a near-Earth object will eventually take us out?
So inevitable on an astronomical timescale. We know things hit the Earth, right? We know that objects collide, but astronomical timescales are very, very, very long, much longer than human timescales. And so, over the next billion years, something else will hit the Earth. But over the next 500 years, it's much less likely. But it's still important that we do look up. And that's why we conduct these surveys, so that we can check and make sure that, yes, we're pretty sure nothing's coming to hit us. But on the off chance we find something that does look dangerous, you want to find it as early as possible. Right? That gives you the best chance to do something about it. So instead of just giving up and saying, well, there's no point, you can do something about it. And that's why we want to look in advance.
If we do the surveys early enough, we actually can find the objects when they're years away from any potential close approaches. And then we have a lot of different options that that become available to us if you have enough time. So that's broadly speaking the goal of the surveys, is to just make sure that there really is nothing headed our way on human timescales, and then give us enough time so that we could plan something to sort of nudge the object out of the way, if in the unlikely event that we ever did find something that is headed in our direction.
Okay, yeah, I was going to ask you, what are these options? You said nudging the object out of the way, or nudging the Earth out of the way. Everybody lean left. Oh, we have a question from Whitney Clavin. How much time would we likely have if we discovered an asteroid of the right size and orbit to destroy a major city? Could something like that happen with just days' notice?
Yeah,
that's Amy.
That is a really important question. And, we saw with the Chelyabinsk impactor, that's an object that we saw with basically no warning at all, partly because the object was really pretty small. At 20 meters, it is a pretty small asteroid, but also the direction on the sky that it came from. So it came from a direction that was pretty close to the sun. And that's a place where we really have a hard time looking with our telescopes because the sun is so bright. So what we're trying to do is build out so that we have more capability to spot objects that are at least as big as Chelyabinsk and larger. Really, we want to focus on things that are kind of roughly, say, 100 meters across and up, because these are the ones that are capable of causing really severe ground damage. And then try to spot them when they're, 5, 10, 20, or even more years away from any potential close approach. So we are trying to do that when we design our surveys.
Right. And one of the things we also do is, as a community of people invested in planetary defense, is there's a conference every few years called the Planetary Defense Conference, where we get together as a community and simulate what would happen if we discovered something and we had 5 years warning or 30 years warning, and it was of various sizes. And so play act these scenarios to figure out who would communicate with who, how do you respond to it, what are your options, and what can you do? So that we can basically test out all of these possible scenarios long before we ever have to worry about it.
Got it.
Yeah.
Okay, that's great. That's great. And I mean, and that's interesting because something big enough to, mess up a city is slightly different than something that will destroy an entire species.
Exactly.
Right. So
and those are easier to spot.
Yeah, we want to try to start with the big stuff, and that's what we've been doing as a community. We've been kind of looking for the really biggest asteroids that are out there and sort of working our way down in size to try to find the smaller and smaller ones as well. Right. So that's kind of been the general plan.
Got it. Okay, now since we started out talking about movies, I'd like to continue talking about movies, because for some reason, asteroids and movies, I mean, it's funny because it's this thing that people are even people who don't necessarily like science fiction, like Michael Bay, find the idea of asteroids or some kind of near Earth object impacting on the planet. They find that interesting, because everybody, even somebody who's terrible at math or physics, can still understand why this is a problem. But I would love to get your scientific expertise view on a couple of movies. And what's your impression? For instance, something like the asteroid field scene in The Empire Strikes Back, which was a long, long time ago in a galaxy far, far away.
Oh, absolutely. That's one of my favorite movies. I love that movie, of course. I mean, it's so great. And, they're flying around the asteroid belt. There's the, cosmic worms trying to eat them in the asteroid belt. I mean, well, okay, a couple things. We don't know of any asteroid worms.
Yeah.
I'm sorry. It's a real bummer. I would love it if we could find asteroid worms. That would be super cool, right? I mean, but we don't know of any of those. Yeah. And the other thing about that, aside from the worms, is that if you were in our asteroid belt, in our solar system, if you were standing on the surface of an asteroid and you were looking out at the other asteroids, you probably wouldn't see a scene that looks like you see in the movie, where there's all these big chunks of rock flying around and you have the Millennium Falcon and you're dodging things. Instead, it would mostly look like a bunch of dots.
Yeah. They're really actually pretty far apart.
Yeah. Even though the asteroids are really big, I mean, they're huge, right? They can be tens or hundreds of kilometers across in some cases, but space is even bigger. Yeah. And so they still look like dots most of the time.
Yeah. So nobody's jumping from asteroid to asteroid.
No.
No, I still am holding out for the space worms, though.
Yeah.
Joe, we got to find a way to find the asteroid worms.
We'll find some space worms.
Oh, yes. Looking for that specific heat signature.
There we go.
All right. Now, another one. Joe, tell me, what do you think about the movie Deep Impact?
I liked Deep Impact. I liked it that it tried to be as realistic as possible as you can be in, a movie setting, obviously. But, it had, the comet coming, and it had, okay, we're going to try a bunch of different things. And we're going to do a bunch of observations and the transmitting the information. It had all this covered, which is why a lot of people think it was the more boring of the two films that came out in that era, because it really did stick to what you can do and not what would be great to see on the movie.
Spoken like an astronomer, Joe.
Boring is good. Our lives, we don't excitement. Excitement is problematic.
That's true.
Well, and the thing is, yes, if something were actually coming at us, we'd want somebody who enjoyed Deep Impact to be making the decisions. It's like, let's sit down and talk and have meetings, as opposed to let's try to build a giant cannon.
I'm going to go for meetings.
Speaking of meetings, Don't Look Up had some meetings. Amy, was that you? Did you tell them you have to have more meetings?
Yeah, it was pretty fun to work on that. We had it be a comet that was the impactor, because in reality, comets, we really do find long period comets. These are comets that come from the very outer part of the solar system. We do discover those sometimes with very little notice, sometimes just a few months before they make their close approach to the sun. So that's very scientifically accurate. However, in general, of course, it takes us a lot longer than just a few months to build a spacecraft. So I talked to Adam, who's the writer-director of the movie, and I said, Adam, it would be really great if we could have like 5 years. And he said, I'm not going to make a movie about 5 years of design reviews. And I said, but come on, 5 years of design reviews would be great. I would watch that. He told me that was a bad idea.
You would be the only one watching that.
Yeah, that's true. You're right. It probably would have been a bad idea. Yeah. But in any event, I tried.
See, okay, sure. Don't Look Up did great on Rotten Tomatoes, but Amy's version would have done great on, I don't know, what do you call it? Rotten PhDs?
Yeah.
The doctors loved it.
5 years of WebEx calls.
It would have been more realistic. Oh, and of course, Armageddon.
I mean, it wasn't at all as realistic as Deep Impact. There were a lot of problems.
You wouldn't try to get oil riggers into space?
No, and then when you get there, the whole thing with the cliffs and it was very contrived. But I will say, I appreciated that it had such a good soundtrack and a cast. It inspired a lot of people. It inspired a lot of the public to care about asteroid impacts. So credit where credit's due. It really, helped push this into the national discussion. So, and there were a lot of explosions. And that's always nice because why else go to the movies if not to watch things blow up?
That's funny. Oh, wait, we have another live question from somebody watching. From Stacy. Ooh, this is a great question. Are there any citizen science projects that could assist toward the survey effort?
That is a great question. There are some citizen science projects, I think, that are going on or that have gone on. They've kind of come and gone over the years. I think there was one that was going on to look at data from, was it, Joe, do you remember, was it Catalina Sky Survey? I think it was.
I think it was Catalina, yeah.
Yeah, I think so. So there's occasionally been some citizen science projects that do that. Also, there have been a lot of efforts to do follow-up of asteroids. So in other words, once we spot the object, that's only in some ways the beginning, right? We want to know as much as we can about it. We'd like to know things like how fast it rotates, what is its shape, how big is it? These are all questions, excuse me, that can be answered through additional observations. And there have been some really talented folks taking data on these through citizen science efforts.
Yeah, I mean, there's a really active community of people out there who are, building telescopes in their backyard and taking data and submitting it alongside the major survey data, and really helping the process. I mean, it's really an important addition to what's being done by the professional surveys. So yeah, there's a lot of room for citizen science in tracking asteroids, watching them, understanding what they are, even just looking at how their brightness changes with time, as they spin and rotate. That kind of stuff really can, help us better understand these objects. And, there's a lot of asteroids out there and we don't know a lot about them. So if you find one thing you can do, I'm going to get light curves for thousands of objects. That's a major contribution.
Okay. So we're telling people, do look up or do not look up. There is no try, but do. All right. Well, thank you, guys. This has been so fascinating. Although I'm now going to get a much bigger umbrella when I go outside. But before we wrap up, I'd like to ask you, are there any final thoughts that you guys would love to share with the audience before we go? Amy?
Okay, sure. Yeah, thanks, Phil. I mean, I would say, well, first of all, it's been an absolute ton of fun to get to talk with you and everybody here. But I think in general, we're really lucky to get to do this work. It's not a problem that you need to be worried about in your everyday life, but we are doing more advanced surveys like the upcoming Earth Object Surveyor mission. We're working on that. And hopefully that will give us a much better understanding of what is out there in our solar system and what, if anything, is headed our way. So that we'll have some idea about what we need to be doing next.
Excellent. Joe, final thoughts?
Yeah, looking for hazardous objects and dealing with the consequences if we find one really is a global endeavor, right? And this conference I mentioned, this Planetary Defense Conference, it's a global conference. People from all over the world come together to work out how we would communicate as a society, right? This isn't just one person or one nation. This really is a global effort, and we do need to work together to be able to address this problem. And so that's really extra important to emphasize.
Well, like they say, safety in numbers, but unity is key, because you're getting information together. And the thing is, we're all in this together, especially when we're talking about, global hazards.
Right.
Exactly.
So that makes sense. Oh, we have a comment from Brandon Priest. Thank you for relieving me from being scared. I love this YouTube channel. I'm permanently staying subscribed to this channel.
Very welcome.
Okay. See, that's why we have Joe on this show all the time, because he gets us subscribers. Oh, got a lot of Christopher McLean. Watch the skies. Oh, thank you guys for the comments. See?
Yeah. No,
if people comment, that means they're paying attention.
Well, as we like to put it, we try to watch the skies, so you don't have to.
Exactly.
Well, you guys are watching much farther past the skies than the rest of us. We're just looking at the blue part.
Well, we try and keep an eye out for what's out there. It's a lot
Yeah.
of fun, and we're just so lucky to get to do the work.
We really are. Yeah. It's as Amy said, yeah, it's really a important thing to do, but I'm grateful I get a chance to do it. Right.
Yeah. And Amy, you get to watch the birds. So if the birds ever cluster together and try to come at us, you'll spot them in time.
Yeah, there's something about moving objects, whether they're on Earth or in space. I don't know what it is, but I like them.
Are you a big fan of NASCAR too? No, it's got to be objects that are up.
Yeah, it's got to be objects that are up.
Once they start flying, then yeah,
Flying NASCAR races.
Flying
Okay, there we
NASCAR.
go.
Ooh. Jetpacks. Okay. Well, thank you guys for watching. And Amy and Joe, thank you so much for joining us today and sharing your knowledge and expertise on this really fascinating subject. Now, folks, you can see this video as well as our other Universe Unplugged, Ask the Astronomers live shows, including Joe's previous show and maybe Amy's next show. We don't know. Just click on the link in the comments there and make sure you subscribe, just like Chris did, and follow us on YouTube, Facebook, so that you'll catch our next really fun show. And until that next show, I'm Phil Lamar. Thank you to Amy Mainzer and Joe Massaro. And this has been Ask the Astronomers Live.
Thank you.
Do look up.